Hi everyone, it's Mr. Pope from Woodson Grammar School for Boys, and today I'm going to be talking about matrices. Now, there's so much to talk about when it comes to matrices. Today, I just want to go over some simple operations, some definitions, just to familiarise yourself with the topic. Just to give you a bit of a crash course in it, really. There's so many applications to it, and the reason I've put matrices in the geometry and vectors component when I was planning this is, well, in all fairness, matrices would fall under a topic that's widely regarded to be linear algebra, although it extends past that in many cases. And should you study mathematics or some kind of mathematical science at university, then I find it incredibly odd that within the first year or probably the first semester you wouldn't be learning about matrices, some linear algebra, that kind of thing. So why have I put it in the vectors and geometry section? Well, mainly because I'm trying to link it towards the geometric applications, not just in terms of linear algebra, although we will be looking at how to solve differential equations using matrices as well at some point, in particular ODEs, ordinary differential equations. So what is a matrix? Well, let's suppose I have this system of equations. Let's say I've got 2x plus 3y equals 10. And then let's say I've got 3x minus 2y equals, what would be a good number? Well, let's think about this for a second. Let's make that 11. Let's make that 10. Okay, suppose I've got a system of equations like so. Then what can matrices do? Well, matrices are essentially just ordered sets of numbers and letters, components. So I could write the following. So I could have something like this, and notice what elements go where and potentially why. So I would have x and y here, 11 and 10 there, and 2, 3, 3 minus 2. Now, can you see that the coefficients are these numbers? Can you see how the x's and y's go into this column, and the answers on the right hand side go here? Now, it's not as obvious as the top row equals the top row and the bottom row equals the bottom row. That's not what's going on here. In actual fact, it's a lot more technical. So, okay, first of all, let's talk about the dimensions of a matrix. That's really important. So over here, this matrix here we would consider to be a 2 by 2. That is because there are 2 rows and 2 columns. Okay, so you can probably guess what we'd identify the next matrix to be. This would be a 2 by 1 matrix because there's 2 rows, 1, 2, and 1 column, dosh. And then finally, the output is going to be a 2 by 1 as well. Now, important thing. Adding and subtracting matrices, then the matrices need to be the same dimension. And the way that works is, suppose I've got a 2 by 2 matrix, let's say A, B, C, D, and I want to add another matrix to it, let's say capital A, capital B, capital C, capital D. then the resultant matrix would be little a plus capital A, little b plus capital B, little c plus capital C, little d plus capital D, right? So each of these individual elements stay in their same orientation within the matrix. This is an element, this is an element, this is an element, this is an element. So if you want to add something, if you want to add a matrix to a 2 by 2 matrix, it must be a 2 by 2 matrix, and so on and so on and so on. When the rows and columns equal each other, this is called a square matrix. Okay, and the other ones are either non-square or rectangular matrices. It's up to you how you want to define them. You cannot add a scalar to a matrix. So what does that mean? So if I've got the matrix, say A, B, C, D, if I was to say plus 1, well, that's just a nonsense. You can't do that. Right? So I can't just add a number to that list. That doesn't really make sense. What I can do, however, is I can multiply scalars by matrices, and that's totally fine. So suppose I wanted to add 1 to that matrix. What I could do is, well, it's not really adding 1, you'll see what's happening. I could, well, first of all, let's introduce this idea called IN, which is the identity matrix. That's n by n. So let's talk about it. I1 would just be a 1 by 1 matrix, which is just a 1. I2 would be a 2 by 2 matrix, which is a 1, 1, and then zeros everywhere else. I3 would be a 3 by 3 matrix, and it's got 1s down the diagonal and zeros everywhere else. And hopefully you're getting the idea now. But I4 would be a 4 by 4 matrix with 4s down the diagonal and zeros everywhere else. Okay, so suppose I wanted to do, if I go back to multiplying scalars by matrices, if I wanted 4 lots of A, B, C, D, then that's just as how you'd expect it to be. That would be 4A, 4B, 4C, 4D. Okay, really easy. Okay, now maybe I've skipped an important step. Why do I need to be able to do this kind of stuff? Well, the original motivation was I've got a set of simultaneous equations and I'm claiming that I can solve them by writing them out in matrix form. Now there's various ways of solving this using matrices, and when it comes to more complex equations, i.e. ones in 3D or as many dimensions as you like, or systems of equations that are just too long and painful to do by hand, then what you want really is to be able to program a computer to do this. And essentially by understanding how to do this, then you know how to program a computer to solve these kind of questions. So let's chat. We've got one more thing. Multiplication. Multiplying matrices. Okay, by the way, you can multiply and divide by scalars. That's totally fine. So if instead of timesing by 4, I want to divide by 4, that's easy. I just times by a quarter, and this becomes a quarter A, a quarter B, a quarter C, a quarter D, in the usual way. That's not, it's not anything crazy. Multiplying or dividing by scalars is totally easy, because real numbers are just like that. However, multiplying and dividing matrices is a different kettle of fish. And this is where dimensions need to be checked. And there's a bit of an odd rule here. So, if I have So it only works if I have an m by n matrix, dimensions, and I multiply by an n by, let's say, p matrix. Then the check is, if these two numbers are the same, then the output matrix is going to have dimensions of an m by p. Okay, and that's really weird. Okay, so in actual fact, what we say is they're not commutative. Okay, so matrix multiplication is not commutative. Okay, that's a really important key fact to get down. So what do I mean by commutative? Well, real numbers, so if I compare this to real numbers, then if I ask you to do 2 times 3, that's the same as 3 times 2, and we're happy with the answer of 6. However, if I've got the matrix A and I multiply it by the matrix B, that is not necessarily the same as the matrix B times by the matrix A. Okay, it's not commutative. The order in which you multiply things absolutely matters. So, let's talk about what's going on up here in the original thing. So I've got two matrices going on. Let's call this the matrix A, let's call this X, and let's call this output B. Right, so when I'm multiplying A by X, I have to check these two. Now, are they the same number? Yes. So that means matrix multiplication is possible, and the dimensions of the output will be 2 by 1, and indeed that is the case over here. So the dimensions of this matrix multiplication work out. Okay, now let's actually multiply some matrices together. So let's go back to this example and see what will happen if we start multiplying matrices together. Okay, so let's have the example here. Okay, now to multiply matrices, a little bit difficult, but once you get the hang of it, it's actually incredibly easy. And the way you've got to remember it is you just have to multiply each element of the rows in this matrix by the columns of this matrix. And let's clarify what I mean by that. So the first thing I'm going to do is I'm going to check the dimensions. So I've got a 2 by 2 and I'm multiplying that by 2 by 1. So that's going to, the 2 by 2, that works out. So it's going to output a 2 by 1. So I'm already anticipating a 2 by 1 matrix. Okay, so I'll call this A11 because that's first row, first column. And this one down here is A21, which means second row, first column. Okay, now what I do is I do first row, first column to get the first row, first column entry in my matrix. And it's very simple. I do 2, I just multiply them individually and then add as I go along. So I've got 2 times x, which is 2x, plus the next one along 3 by y, so plus 3y. Okay, now that's that one done. Now I've run out of that row and column, so now I move down to the next item. So that's the second row, first column. So I go second row, first column. So I do 3 times x, first of each. So first of that row, first of that column. So 3 times x will be 3x. And the second item of that row, second item of that column, minus 2 times y is minus 2y. And lo and behold, this 2x plus 3y and 3x minus 2y is exactly what we wanted up here. Can I zoom out a little bit? Yeah, the top left, I wanted 2x plus 3y, which is what I've got. And I needed 3x minus 2y, which is what I've got. And that will equal what I'm claiming it equals to, which is 11, 10, like so. And now at this point, because they're both 2 by 1 matrices, I can just read across the top and read across the bottom. So I'm hoping that's convinced you that they're the same. Let's go through another example. Let's go through another example of matrix multiplication, and hopefully I can show you what's going on here. So let's try a different pair. So let's suppose I've got 2, 1, 3, 2 multiplied by 3, 2, 1, 1, 2, 3. Okay, well, let's think about this one. I've got a 2 by 2 matrix here, and I'm multiplying it by a 2 rows by 3 column matrix here. I check these two numbers. They're the same, so this matrix multiplication will work, and it'll output a 2 by 3 matrix. So I know it's going to output 1, 2, 3, 1, 2, 3. It's going to produce 2 rows by 3 columns. Okay, so let's do this step by step. So for the first row, first column, I take first row, first column, multiply them and add them as I go along. So I'm going to have 2 by 3, which is 6, plus 1 times 1, which is 1. So 6 plus 1 will give a 7. Okay. Let's do first row, second column. So we do first row, second column, and we just multiply and add as we go along. So 2 times this 2 is 4, plus 1 times 2 is going to be a 6. So that is a 6. And then for the last bit of that row, that's in the first row, third column. So first row, third column, and we multiply corresponding elements. So 2 times 1, 2 times that 1 is 2, plus 1 times 3 is 3. So 2 plus 3, that will give a 5. Okay, for this element here, that's in the second row, first column. So second row, first column. So we're going to do 3 times 3, which is 9, plus 2 times 1 is 2. 9 plus 2 is 11. So that is 11. For this element here, that's the second row, second column. So second row, second column. So we'll do 3 times 2, which is 6, plus 2 times 2, which is 4. 6 plus 4, that will give a 10. And then finally, this is the second row, third column. So second row, third column. So we're going to have 3 times 1, which is 3, plus 2 times 3 is 6. 3 plus 6, that will give a 9. And I've now successfully completed this matrix multiplication. However, suppose I was to swap the order of this. So it's now 3, 2, 1, 1, 2, 3, multiplied by, and I won't do the multiplication symbol, 2, 1, 3, 2. Then look, this is a 3 by 2 matrix. This is a 2 rows by 3 columns, and this is multiplied by a 2 by 2. And now look, when I compare these two, they're not the same number, so this can't happen. So this will not produce anything. Okay, the order in which you multiply matrices matter. So in this case, it does produce something, namely this matrix here. However, when I swap the order of them, it doesn't even make a matrix at all. Now, for a final example, let's take 2 square matrices and see what happens there. So let's have 1, 2, 1, 3, and then let's multiply that by 2, 1, 2, 1, and see what happens. So again, this is a 2 by 2 multiplied by a 2 by 2. The 2's inside are the same, so it's going to output a 2 by 2, so we're expecting a 2 by 2. So here, first row, first column, first row, first column. I've got 1 times 2 plus 2 times 2, which I believe is going to be a 6. I've then got first row, second column, first row, second column. I've got a 1 times 1 plus a 2 times 1, so that's going to give a 3. Then I've got second row, first column, so second row, first column. So I've got 1 times 2 plus 3 times 2, which I believe is 8. And then in the last column, second row, second column, second row, second column. So I've got 1 times 1 plus 3 times 1, which I believe is a 4. Right, now let's swap the order of these matrices. So I've got the 2, 1, 2, 1 there, and I've now got the 1, 2, 1, 3 here. So I've now swapped the order. So if this was A, this was B, I'm now going to compute B, A, like so. Okay, same deal. This is a 2 by 2 and a 2 by 2. So these two numbers are the same, therefore they're going to output a 2 by 2. Here it is over here. So first row, first column, first row, first column. 2 times 1 plus 1 times 1 is going to give a 3. Then first row, second column. So first row, second column. I've got 2 times 1 plus... Sorry, I've got a 2 times 2 plus a 1 times 3. It's 4 plus 3, so that's going to be a 7. And then second row, first column, second row, first column. We've got 2 times 1 plus a 1 times 1, so that's going to be a 3. And then second row, second column, second row, second column. We've got 2 times 2, which is 4, plus a 1 times 3. I believe that's just going to be a 7 again. Okay. Have I done that right? Yeah, seems to be. Okay. And clearly this matrix is not the same as this matrix. They have different elements pretty much everywhere. So I'm hoping you can agree that AB doesn't necessarily become BA. There may be special cases where it does actually equal. So yeah. You just have to be really careful. Now, you're probably thinking, okay, fine. So this does represent what's going on here. So how can I use that? What's the point? Well, we're going to have to actually do some stuff here. So ignore the matrix for a little bit. Now, I defined this thing up here as the matrix A times by X times by B. Sorry, matrix AX equals B. So let's think about that for a second over here. So I've got the matrix A, I'm timesing it by X, and that equals the matrix B. Now really, I want to solve for X. So what would I do both sides? Well, if these were numbers, I would just do B divided by A, and that would give me X. The problem is we can't divide by matrices. So what we're going to have to do is we're going to have to find what's called the inverse of A, which is kind of our way of getting around by dividing by matrices. So if I apply the inverse of A to both sides, then inverse of A from the left, inverse from A from the left. So imagine the matrix slides in from the left both sides. And as we said before, the order in which you multiply matrices matters, so you're going to have to imagine that letters slide or matrices slide in from the left or right. Now that means if I've got A times X by the inverse of A, if I'd slid it in from the right, then this isn't necessarily going to cancel out or do anything. However, if I've got the inverse of A times by A, then this is going to just equal the identity matrix. Okay, the identity matrix is kind of like the matrix version of 1. And 1 times anything is just going to give X. So what we're saying is if I multiply B by the inverse of A, I will solve for X. And now there's multiple ways of finding the inverse of matrices. And essentially you can only do this for square matrices. And also matrices that are considered non-singular. And I'll talk about that in a second. So, okay. What do I mean by non-singular matrices? Well, to answer that question, we're going to have to consider something called the determinant. Okay, and it's really easy. If I've got a matrix A, B, C, D for a 2 by 2, then the determinant is this product. So the determinant of this thing is A times D minus the opposite product, B times C. And that's easy to compute. So if I had 2, 1, 3, 1, then the determinant of this would be 2 times 1, which is 2, minus 1 times 3, which is 3, 2 minus 3, that's just going to be negative 1. Okay. Easy to compute. And essentially, a singular matrix has a determinant of 0. So because this matrix here has a determinant of negative 1, and this is a non-singular matrix, and therefore it will have an inverse. And that's fine. That's totally fine. Now this trick works for 2x2s. For 3x3s, however, well, we've got to be a bit more creative. So, oh boy. Okay, so let's suppose we've got A, B, C, D, E, F, G, H, I. Now, instead of writing a formula, what I'm going to do is show you the general gist of it. Because once you do, you can spot how to find determinants really easy. And the first thing you've got to do is imagine there's a checkerboard. Okay, they're alternating signs. So imagine this checkerboard goes plus, minus, plus, minus, plus, minus, plus, minus, plus. Like so. Imagine a checkerboard. And now what you do is you can take any row, any column, doesn't matter. So say, for example, I take this row here. Then what you do is you're going to have plus A, lots of a determinant, minus B, lots of another determinant, plus C, lots of another determinant. And what goes in this block is going to be the mini determinant, as if you crossed out the A row and the A column. So you've got to find the determinant of this thing. So you can ignore the plus and minuses now. So it's going to be EI minus FH. Okay. And then for the B, well, you cross out the B row, the B row, and now the B column. And now you have to take the determinant of, imagine these two things were squished together. So it would be one diagonal, DI, minus the other diagonal from top right to bottom left, which is FG. Okay. And then the final one for C, then you block out the C column and C row, and you take the determinant, this 2x2 determinant of this. So you're going to have DH minus EG. And that's it. So, pro tips with a 3x3 matrix is you want to ideally pick a row or column with as many with as many zeros as possible to make it easy. For example, if I had, say, the 3x3 matrix, let's say I want to find the determinant of the 3x3 matrix, which is 1, 2, 3, 0, 1, 0, 5, 6, 7. Then my obvious candidate would be to use this row because there's 2 zeros. Why is that good? Because if I have the checkerboard, remember plus, minus, plus, minus, plus, minus, then I know the determinant of this thing is going to be minus 0 of a determinant, which is nothing, plus 1, lots of something, the determinant when I cross out that column and row, minus 0, so then I don't have to include that either. So now all I have to do is find the determinant when I block out this one and this one. So I'm going to have 1 times 7, which is 7, minus 3 times 5 is 15, 7 minus 15, the determinant appears to be negative 8. And that could have been a really long-winded process, but actually you can really eat through it when you know a few tips and tricks. So yeah, it's one of those things. How does the determinant relate to the inverse? Well, bit of a sidestep, because if I've got, so if I want to inverse a 2 by 2 matrix, okay, then the inverse of A, if A is A, B, C, D, like that, then the inverse of A is 1 over the determinant of A. So notice how that kind of realizes why you can't have an inverse of a singular matrix, because you'd be dividing by 0 at that point, because 1 over 0, yeah, it wouldn't work. And then the matrix you have to times it by, because remember we're looking for a matrix, is you swap. You swap the top left and bottom right. So instead of A being in the top left, it's now in the bottom right. And instead of D being in the bottom left, bottom right, it's now in the top left. So notice how these two have now swapped positions. And then what's really easy is you just make the opposite corners just the negatives of what they were. So in my previous example, say I had, what was it, 2, 1, 2, 1. Was that one of the ones I had? Yeah, 2, 1, 2, 1. Okay, first of all, if this is matrix B, is there even an inverse? Well, 2 times 1 minus 2, 1 times 2 is just a 0. So no, there is no inverse, because the determinant of B is 0. It's a singular matrix. However, if I look at the other example I had, which is 1, 2, 1, 3, back up there, let's call matrix C 1, 2, 1, 3, then let's suppose I try and find the inverse of that. Well, the determinant is 1 times 3 minus 2 times 1, so it's going to be 1 over that determinant, which is 1. And then the matrix is going to be the 1 and 3 swap over, the top left and bottom right, so that becomes 3 and 1. And then the 1 and 2 in the other corners become negative, like so. And then since 1 over 1 is just 1, then I can times everything in here by 1. So the matrix inverse is just going to be 3 minus 2 minus 1, 1. And then finally, let's check that C times by inverse of C, which should be the same as the inverse C times by C, does equal the identity matrix 2 by 2. Well, let's do 1, 2, 1, 3, multiply that by 3 minus 2 minus 1, 1. Same deal, rows, columns. So first row, first column, first row, first column. 1 times 3 plus 2 times minus 1 does equal a 1. Good start. First row, second column, first row, second column. We've got 1 times minus 2, which is minus 2, plus 2 times 1, which is 2. Minus 2 plus 2 does equal a 0. Good, looking good so far. Second row, first column, second row, first column. You've got 1 times 3 plus a 3 times minus 1. So yes, that does equal a 0. And then second row, second column. We've got second row, second column. We've got 1 times minus 2, which is minus 2, plus 3 times 1. So minus 2 plus 3 does equal a 1. And this is indeed the identity matrix with 1s down what's called the leading diagonal and 0s elsewhere. If you want to, you can prove this as well. I'm not going to go through it because hopefully you should see that it's true. Okay, now inverting 2 by 2s, really easy. Inverting 3 by 3s. Now that is another pickle. So inverting 3 by 3s. Oh boy. Okay, so here's my matrix. Let's call it capital A, and it's A, B, C, D, E, F, G, H, I. Okay, step 1 is find the determinant of A. Now that's that long-winded process over here where you do the checkerboard thing and you do all that stuff. Right. Step 2, okay, is you have to do what's called, you find the matrix of minors, okay, which is essentially the determinant for each element replacing that element. Okay, we'll get on to that. Step 3 is you then change it into the matrix of cofactors by applying the plus minus alternating sign checkerboard thing. And then step 4, we have to do something called transpose the matrix. And what that means is we keep that diagonal the same, and we flip this side over to here and all of these elements down to here, as if there was a mirror about the diagonal. Okay, and then the final part, which is a part of this, is we take that determinant and we whack it in front of that as 1 over the determinant of the original matrix. So in actual fact, it's probably just better with an example. So let's do this one over here. Right, so I know already the determinant is -8. That's great. So that's step 1 done. Next, find the matrix of minors. Okay, so 3 by 3 matrix. Okay, so imagine for this element, we cross out the row, cross out the column, and we consider the determinant of this thing. So it'll be 1 times 7 minus 6 times 0. So that will just be 7. So I'll put a 7 up here. Then for this element, I cross that out, and now I have to do 0 times 7 minus 0 times 5, and that's clearly going to be a 0. So that element is 0. Then for the 3, I do 0 times 6 minus 1 times 5, so 0 minus 5, so that's just going to be -5, so -5 goes in here. Then for this element, I cross out the column and row, so I'm going to have to do 2 times 7, which is 14, minus 3 times 6 is minus 18, so that's going to be a -4. Okay, and then for this one, cross out, and I've got a, well, I know what this is. I've got a 1 times 7 minus 3 times 5, so that's just -8. That's easy enough. And then for this one, I've got a 1 times 6 minus a 2 times 5, so I've got 6 minus 10, so that's a -4. For this one, I've got that row and that row, so I've got a 2 times 0 minus a 3 times 1, so that's -3. For the 6, which is here, I've got a 1 times 0 minus 3 times 0, so that's just a fat 0. And then for the 7, I've got that column and that row, so it's 1 times 1 minus 2 times 0, so that's just a 1. Okay, a bit long-winded, but there is my matrix of minors. So that's step 2 done. Step 3, the matrix of cofactors, so I change and make a plus minus checkerboard. So that becomes plus minus and -5 stays the same, but -4 makes that a plus -8 keeps it negative, -4 makes that positive. That's a plus -3, so that's fine. Minus a 0 stays the same, +1. So the signs, the matrix of minors now becomes this, which is fine. And then finally, to transpose it, I just times this by 1 over the determinant, which is -8. So another way of thinking about this is I'm going to multiply every element in my matrix by -1 over 8. So what would happen there? Well, 7 would become -7/8, 0 would still stay 0, 5 would now become +5/8, 4 would be -4 over 8, which is -1/2. Minus 8 divided by minus 8, that just become a positive 1. 4 divided by minus 1/8, this is going to be minus a half. Minus 3 divided by minus 8 is just going to be positive 3/8. 0 stays the same, and 1 will just become minus 1/8. So, I mean, you don't have to put it all in, but this now apparently is the inverse of that matrix we had up there. So I don't know, if we call this matrix E, say, then this is the inverse of E. One thing you can do to check that you've done the right thing is you can use your calculator. I'm going to do mine. So math vector, let's have matrix A. Let's have dimensions, let's have it 3 by 3. And let's have that 1, 2, 3, 0, 1, 0, 5, 6, 7. Save it as matrix A. Exit. And now I'm going to define matrix B. And this is a 3 by 3. And I'm going to have minus 7 over 8, 0, 5 eighths. Oh, God damn, that's a 0. That's 5 eighths. This is minus 0.5 or a half. That's 1. That's another minus a half. 3 eighths. This is 0. And this is minus 1/8. Now if I want exit, how do I go back? Matrix, no, exit. Right, I want math, matrix, 3 by 3. Oh, I could have just typed it in there, you silly boy. How does this work? Matrix A times by matrix B? No. Matrix. How do I do stuff? Option. Let me just figure this out. Hello? Is this working? Yeah? Ah, there was a step I've done wrong. Where have I forgot to transpose the matrix. So for the transposition matrix, I don't have to worry about the plus minus stuff because some symmetry. I take that matrix and then I need to swap these elements, swap these elements, and swap these elements. So really, then 0 and minus half should be swapped. So that's minus half and that's 0. The 3 and the 5 will cancel, so that's 5 and that's 3. And then this should be 0 minus half. Like so. Right, apologies. That is the final matrix. Sorry, I completely forgot to do the transpose, the bit at the end. To be honest, the 3 by 3 matrix stuff, such an absolute nightmare. To be honest, I'll show you another method. It's one I use a lot. It's called Gaussian Elimination. And to be honest, let's double check that we've done this right. Your calculators will be able to do this fairly quickly, but you know, just to prove that this will give the identity matrix, let's write these two things down. So I've got 1, 2, 3, 0, 1, 0, 5, 6, 7. Is that? Yep. And I'm claiming that if you multiply that by minus 7 eighths, minus 1 half, 3 eighths, 0, 1, 0, and then this is 5 eighths, minus 1 half, minus 1 eighth. Okay, so just to hammer the point home, why not? So, does this work? Well, this is clearly a 3 by 3, and we're multiplying by 3 by 3. These two are the same, so it's going to output a 3 by 3. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right. First row, first column. First row, first column. So I've got 1 times minus 7 eighths. So minus 7 eighths plus 2 times 0 plus 3 times 5 eighths. 3 times 5 eighths is 15 eighths. Minus 7/8 plus 15/8 is an eighth, is 8/8, so that's just 1. So that works. Good start. Okay. I don't need all these underlined things. You can get it's a 3 by 3. First row, second column. First row, second column. I've got 1 times minus a half, which is minus a half. 2 times 1 is 2. So minus a half plus 2 is now 3 halves. And 3 times minus a half is minus 3 halves. So 3 halves plus minus 3 halves is going to be a fat 0. And then first row, last column, first row, last column. I've got 1 lots of 3/8, which is fine. I've got 2 lots of 0, so we're still at 3/8. And 3 times minus an eighth is minus 3/8, so they're going to cancel out to be a 0 as well here. Now, I could do the other 6 calculations and you could see that unfold. But if I've done this right, then you should get 0, 1, 0, 0, 0, 1 with this leading diagonal of 1s. Okay, incredibly important. Okay, so that's pretty much it for matrices. Now you're probably answering, hold on a minute, you did all this stuff, but you never actually solved the original question. Well, let's do that really quickly then. So for a 2 by 2 matrix, that's really easy. So 2, 3, 3 minus 2. So if I had them, so if I'm solving this one up here, I've got 2, 3, 3 minus 2. I need to find the inverse of that. So I do 1 over the determinant. So 2 times minus 2 is minus 4, times 3 is 9. So minus 4 minus another 9 is going to be minus 13. And what I do now is I swap the diagonals. So this becomes minus 2, 2. And then I change the sign of the others. This is minus 3, minus 3. And now I need to say, well, if ax equals b, then x equals the inverse of a times by b. So what I need to do is 1 over minus 13 of minus 2 minus 3 minus 3, 2 multiplied by b, which in our case is 11, 10. So by doing this, I will get the value for x and y over here. So first of all, does this work? Well, I've got a 2 by 2 multiplied by 2 by 1. These two are the same, so it's going to output a 2 by 1. 1, 2, there it is, the 2 elements. So first row, first column. So I've got minus 2 times 11, which is minus 22, plus minus 3 times 10, which is minus 30. So minus 22 minus 30 is minus 52. So I'm going to have a minus 52 here. But I'm dividing by minus 13, and minus 52 divided by minus 13 is going to give positive 4. Okay, next row, next column. I've got minus 3, 2, and 11, 10. So I've got minus 3 times 11, which is minus 33, plus 2 times 10 is 20, minus 33, plus 20 is minus 13. Minus 13 divided by this minus 13 out front means I'm going to get positive 1. So I can give that x is 4, y is 1. And indeed, looking back at the original question, up here, if x is 4, y is 1, then is 2 lots of 4, which is 8, plus 3 lots of 1, 11? Yes, it is. And is 3 lots of 4, 12, minus 2 lots of 1, 10? Yes, it is. Now, you're probably thinking, okay, well, that just seemed like an awful lot of fuss just to solve some really simple simultaneous equations. And I totally agree. The difference is what happens if you want to solve 3 by 3 or 4 by 4 or 5 by 5 and 6 by 6 and 7 by 7 and so on and so on and so on. And I promised before you go, now there isn't a technique for finding inverses of 4 by 4s and 5 by 5s and so on. What you have to do is something called Gaussian elimination. And you won't learn this until university, but it's really easy. Now this might not be considered Gaussian elimination, actually, thinking about it technically. But essentially what we're going to be doing is elementary row operations on an augmented matrix. So here's the rule of the game. So what was the matrix we were trying to invert? It was 2, 3, 3 minus 2. Okay, so imagine I've got the matrix 2, 3, 3 minus 2. And the augmenting matrix, I'm going to imagine there's a dashed line here, and I'm going to put the identity matrix of the same dimensions on there. So it's 2 by 2, so I'm going to put a 2 by 2 identity here. Now I'm going to perform elementary row operations until this side looks like an identity matrix. Okay, and then the idea is that once I've done to the left-hand side and made it an identity matrix, the right-hand side, if I've done the same thing, will now look like the inverse. Okay, so what do I mean by an elementary row operation? I am allowed to multiply and divide by scalar, i.e. the rows. So the rows I can multiply and divide by scalars, and I can add or subtract multiples of rows. So first thing I'm going to do is you don't have to write this, but I'm going to divide row 1 by 2. And the reason for that is because 2, 3 becomes 1, 3 over 2. And that's immediately looking good because I'll have a 1 in the top left-hand corner. And then just to make the bottom one a 0, I'm going to divide row 2 by 3 as well. So this becomes a 1 and this becomes minus 2/3. What will happen is this becomes 1/2, this becomes 0, this becomes 0, and this becomes 1/3. Now why is this good? Because I can now subtract, I can now do row 2, the new row 2 minus row 1. So row 1 stays as it is, so that's 1, 3, 2. Let's make a distinction, that's 1, that's 2. So row 1 will stay as it is, so that's 1/2, this is 0. And now if I do the 1 minus this 1, I'll get a 0. And if I do minus 2/3 minus 3/2, well, let's think about this. I've got minus 4/6, and I'm going to minus 9/6. I believe that's minus 13/6. So that's minus 13/6. Is that right? Seems legit to me. And then over here, I've got 0 minus 1/2, which is minus 1/2, and this is going to be a 1/3. Okay, now what can I do? Well, if I now take row 2 and divide it by, I'm going to take row 2 and I'm going to divide it by minus 13 over 6. This becomes a 0, 1, which is what I wanted. Now, dividing by minus 13, timesing by 6, dividing by 6 is the same as timesing by 6. So minus 1/2 times by 6 is going to be minus 3. Times by minus makes that a 3, so this is going to be 3/13. And then 1/3 times by 6 is going to be 2. Divided by 13, this is going to be minus 2/13. And now on the top, I've got 1 3/2 still. And then this is 1/2 0. Okay, now it's looking good. I've got most of it right. I just have to worry about this thing. But that's easy enough to do because now all I have to do is row 1. I have to do row 1 minus 3/2 of row 2. And now I'll get 1 0 0 1, which is what I wanted. The bottom row here is still 3/13 minus 2/13. But now, well, let's think about it. This row, if I times by 3 over 2, will become 9/26, and minus 2/13, so times by 3 over 2, will be 6/26. Is that right? Minus 6/26. Right, so I need to do 1/2, which is 13/26, minus the 9/26, which is 4/26, which is 2/13. And then I have to do 0 minus 6/26. 0 minus minus 6/26, which will be positive 6/26, which is 3/13. And now this thing is the inverse. And if you look very carefully, they're all over 13. So this is the same as 1 over 13 lots of 2, 3, 3 minus 2. And if we squint our eyes over to here, look, I've got a minus out front, but if I'd taken that minus away and put it in here, that'd be plus, 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 minus. So 2, 3, 3 minus 2 all over 13. And what do we have here? 2, 3, 3 minus 2 all over 13. Now, this looks really long and lame, but essentially this is what computers do, and they do it a lot quicker than I do it, and you can also program computers to do this really well. And the trick of it is for Gaussian elimination, you always divide by the first term to make sure the first terms become 1. Then you subtract all other terms from the first, or rather you do all other terms into the first, sorry. So you're left with 1 and then a bunch of zeros with a bunch of stuff. And then once you've got that sorted, you then you divide this one, so this becomes a 1, and then these are all 1s, and you subtract them, so this is all zeros. And then you keep going, so you're constructing 1s down the diagonal and zeros down the bottom left. Then once you've got it like that, row echelon form I believe it's called, then you back substitute and solve. Or you can subtract, you can back subtract. Yeah, not particularly difficult. Another way of looking at this is if we'd taken this original thing up here, I could have taken this, so 2, 3, 3 minus 2. Suppose I could have solved this like this. I could have set it up as 2, 3, 3 minus 2, augmented matrix, and this is 11 and 10. And then when I've done row operations, that this becomes 1, 1, 0, 0, 1 down the diagonal and so on, then this would have been fine. So let's deal with that. I divide the top one by 2, so I get 1, 3 over 2. Divide 11 by 2 is 11 over 2. Divide the bottom by 3 to get 1 minus 2 thirds, and then this becomes 10 thirds. I then will try again, and now I have 1, 3 over 2, 11 halves here. But this time I will subtract the bottom from the top. So this becomes a 0. Minus 2 thirds, minus 3 halves. I believe I've done that already. That would just give minus 13 over 6, right? It's the same operations as before. And 10 thirds, which is 20 over 6, minus 11 halves, which is 33 over 6, is going to give minus 13 over 6 here. And now this is nice, because I can divide the bottom row by minus 13 over 6. So the bottom row will become 0, 1, 1. And then the top row will be 1 minus 0, which is 1. And then, well, you just multiply, you just do row 1 minus 3 halves of row 2. So 3 halves, well, this has to be a 0 by default. So what is 11 minus 3 halves of 1? Sorry. So what's 11 halves minus 3 halves? That's just going to be 8 halves, which is 4. And now we can read off. The first thing, which was x, is going to be 4, and then the second variable y is going to be 1. And you can just read them off like that. Anyway, I hope this is fairly useful. I'm going to go through some examples. Again, pause the video if you feel that you can have a go. But here's the first one. Pause it, give it a go. Okay, given that x equals that matrix where a is a constant and a does not equal 2, because if it was, then it would be singular, then find the inverse of x in terms of a. Okay, so the inverse of x is just where you have the matrix, you switch the left, top left and bottom right diagonals, so it's minus 1 and 2. You change the sign of the top right and bottom left, and you have 1 over the determinant on the outside. So this is going to be 2 times minus 1, which is minus 2, minus a times minus 1, which is minus a. So minus minus a becomes plus a. So the inverse is just going to be 1 over a minus 2 times by that matrix there. So it's relatively straightforward. Okay, given that when you add the two matrices, it equals the identity, find the value of a. Okay. Right, so let's suppose I've got 2a minus 1 minus 1, and I'm adding minus 1 over a minus 2, if I take that scalar inside, and minus a over a minus 2, 1 over a minus 2, and 2 over a minus 2. And this must equal 1, 0, 0, 1. Okay, so for a start, if I add these two together, that is terrible. If I add these two together, so this one and this one, they should equal 1. So 2 add a minus 1 over a minus 2 needs to equal 1. If I times everything by a minus 2, I get 2 lots of a minus 2, minus 1 equals a minus 2. 2 lots of a is 2a, 2 minus 2 is minus 4, and this minus 1 make minus 5. So if I add 5 to both sides, that's 3. If I minus a from both sides, a equals to 3. Right. If I substitute that all in, let's see if that works. So if a is 3, I'm going to have the matrix 2, 3, minus 1, minus 1. And plus, on the other side, I'm going to have minus 1 over 3 minus 2. So it's minus 1 over 1, which is 1. A minus 2 is just going to be 1. So you're going to have minus a, which is minus 3. So that's going to be a 1. And 2 over 1, that's 2. Does that equal 1, 0, 0, 1? Well, 2 add... Okay, it's a minus 1, isn't it? 2 add minus 1 is 1, that's right. 3 add minus 3 does equal 0. Minus 1 add 1 is 0. And minus 1 add 2 is 1, so that works out. So yeah, a is 3. Okay, nice. Okay, next question. Well, hold on a second. Transformations we're going to do at some point. Well, we're going to do it next time, so you don't have to do that one. Sorry, I thought I deleted that. Okay, so the matrices A, B, and C are given as follows. It's given that the matrix D equals C times A and the matrix E is D times B. Find D and show that E is that. If you want to pause the video and give it a go yourself, I'm going to go through it in a minute. Right. Okay, find D. So what is D telling me to do? D is telling me to do C first and then A. So C is 1 over root 2, minus 1 over root 2, 1 over root 2, and 1 over root 2. To be perfectly honest, to speed things up, I'm just going to take a factor of 1 over root 2 out and have this as 1 minus 1, 1, 1. And then if I times it from A, then again, I can take the 3, I look at this, and this is just 3 root 2 lots of 1, 0, 0, 1. Well, what's going to happen here? This is the identity matrix, so multiplying by that does absolutely nothing. 3 root 2 times 1 over root 2 will just cancel down to 3. So I've actually got 3 lots of 1 minus 1, 1, like that, which is actually 3 minus 3, 3, 3. So that matrix there is D. So that's fairly straightforward. E is D times B. Okay, so all I have to do is find D, which is what I've got. So 3 minus 3, 3, 3. And this is, so just to find out what E is, that's D. And then B comes in from the right, which is 0, 1, 1, 0. Okay, so first row, first column, so 3 times 0 plus minus 3 times 1, that's going to be a minus 3. First row, second column, that's going to be 3 times 1 times, that's going to be a 3. Second row, first column, that's just going to be a 3. And then second row, second column, that's going to be a 3 as well. So just a -3 in the top right. Yes, it does. Bosh. Okay, that's it. Yeah, fairly straightforward. Okay. Now, I've left this part in here because I might want to talk about it, but only just do parts A and B. So pause the video, give it a go yourself. Okay, so the dreaded 3x3. Okay, first thing of all, I need to find the determinant of this thing. So because there's no zeros, it doesn't really matter which one I do. So I know the determinant of m is going to be 2 lots of the determinant of that. If I take this row, minus 1 lots of the determinant from 1, plus a -3 lots of the determinant from that one. So from the 2's perspective, I've got -2 times -2, which is 4, minus a 5, which is -1. So I might as well be putting a -1 there. And when I'm thinking about my matrix of minors, then I'm going to put a -1 there because I've already done that. Next up, for this one, then I've got 4 times -2, which is -8, minus a 1, which is -11. So I'm going to put a -11 there as well to save some time. And then for here, I've got 4 times 5, which is 20, minus a -2 times 3, so 20 plus 6 is 26. So I'm going to put a 26 there, and then we're done. Right, so what's the determinant? I've got 2 times -1, which is -2. I've got -11, which is +11. And I've got -3 times 26, which is -78, isn't it? Calculator time. So what's that? -80 plus 11. That's just -69. Okay. Now I'm looking at the matrix of minors. So from the 4's perspective, I've got 1 times -2, which is -2. Minus 3 times 5, so that's plus a 15. So that's going to be a 13. From the middle, I've got -4 minus a -9. So -4 plus 9 is 5. And then, what am I looking at? And then, yeah, the last one, I've got 5, 10, sorry, -3. So that's 7. And then from this one in the bottom left, I've got a 1 minus a +6. So I'm going to have -5 there. And then I've got 2 minus a -12. So that's 14. Dear me. And then I'm going to have a -4 minus another 4, which is going to be -8. Okay. So I've got my matrix of minors. I need to alternate signs, so that becomes plus, minus, plus, minus, plus, minus, plus, minus, plus. Okay, so nothing really changed apart from the 11. And now I need to transpose it, so the -1, -1, 5, -8 stays the same. That's -13, that's 11. That's -5, the 26 flops over. This is -14, this is -7. And this all has to be divided by -1/69 to get the inverse. I'm just going to use my calculator to check that's right. So matrix, let's introduce a matrix. It's my matrix C. It's a matrix 3x3. And it's 2, 1, -3, 4, -2, 1, 3, 5, -2. That's cool. And now I want math, no, hold on. I want math, matrix, no, yes, no, math. No, how did I do this? Menu, run matrix. Okay, let's have my 3 by 3. 2, no, come on, 2, 1, minus 3. 4, minus 2, 1. 3, 5, minus 2. And I want the inverse of that, so that's the power of minus 1. Oops, minus 1. Okay, a lot of things over 69, so... Okay, yes, 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 yes. That's just definitely a 7 down there. Let's not get confused, that's definitely a minus 7. Yeah, that's fine, and then yes, okay, cool. So I've used my calculator to check my answers right. Seems legit to me. And now I'm going to solve the following simultaneous equations. So I notice that if I write this in vector form, this is 2, 1, minus 3, 4, minus 2, 1, 3, 5, minus 2, lots of x, y, z, and this equals minus 4, 9, 5. So I know now that actually to get x, y, z, I just multiply by the inverse, which is what I've done, minus 1 over 69, lots of minus 1, minus 13, minus 5, 11, 5, minus 14, 26, minus 7, minus 8. So if I take that answer and I multiply by matrix, no, yes, and I want, what is it? It's a I want, that is a 3 by 1. Yes, and in there goes minus 4, 9, 5. Okay, so apparently this spits out minus 52, 117, and 65. Wow, okay. Well, let's just check it. Let's go back then. So, how do we check that? Well, we just sub it in. So 2 lots of minus 52 plus y, which is 117, minus 3 lots of 65 is minus 182. My calculator has not done the business here. Okay, well, I've not done this properly then. It's because I used the answer key. Maybe I have to, I have to type the matrix in again. This is wrong, so it's good to check your answers. I was supposed to do the inverse of that times by the minus 495. So math vector, let's have, no, I don't want that. Let's have math vector, so m by n, dimension 3 by 3. And in there, we're going to have 1 over 69. And the next element is going to be 13 over 69. And the next element is going to be 5 over 69. The next element is going to be minus 11 over 69. And then putting the minus in, that's minus 5 over 69. And the next element is positive 14 over 69. And the next element is minus 26 over 69, and then positive 7 over 69, and then positive 8 over 69. And I want to multiply this by a 3 by 1 matrix, where that is minus 4, 9, 5. That's more like it. It's giving me the answers of 2, 1, 3. So let's check it now. 2 lots of 2 is 4, plus y, which is 1, minus 3 lots of 3 is minus 9. 4 plus 1 is 5, minus 9 is minus 4. Yeah, okay. We've got the right deal now. Okay, so there we are. So solve it. So it looks like x is 2, y is 1, and z is 3. I could have just done this, but I used my calculator instead. Your calculators should really be FX CG50s by the Casios or FX991EXs. Yeah, they're white. One's £30, one's £100 or so. They're definitely worth it. The £30, the 25 the 25 to £30 one is usually all right for all this kind of stuff. Right. So, part C: interpret the answer to your thingy geometrically. Okay, so we haven't actually covered this yet, but what I've got is these three objects. Okay, these are three geometric objects. Doesn't matter what they are for now, but what I know about them is that they all meet at a point. Okay, there is a solution to them. All of those objects meet at one point. So it doesn't matter if they're lines or planes. So if I've got a plane looking like that, and I've got another plane looking like that maybe, and I've got another plane kind of shifting like that, and they all meet in the middle kind of thing at one particular point. Quite hard to illustrate, I suppose. But I'll tell you what, I was going to save this for another time. But what we've got going on, I think, is something like this. So what we've got is if we've got three objects, well in this case they're planes, spoiler alert, but they're planes, we've actually got something like this going on. We've got the three planes are intersecting at that point in the middle. So they're meeting at a point. You know, I don't rate the Edexcel textbook particularly well. I think it's littered with mistakes. I think they don't explain things particularly well, or they're just straight up wrong. For example, with the interpolation. I think they needlessly complicate things. But one of the things, there's quite a few good things they do in all fairness. It's not all bad. But one of the good things they do, I feel, is this these diagrams in the Defer the Pure core book, and I'm going to show them next time we talk about like graphical representations with vectors and matrices, and how transformations can be expressed as matrices and the rest of it. But yeah, to me this set of sequence of diagrams just really explained it to me particularly well. I don't know whether you find them useful or not. It's up to you. We'll talk about them more. Right, is this the last one? Yes, it's the last one. Okay, I seem to remember I picked a doozy for this one. So, okay, matrices, the final frontier. I believe this was last year's further maths AS paper question on matrices. I can't remember. Anyway, the population of chimpanzees in a particular country consists of juveniles and adults. Juvenile chimpanzees do not reproduce. Okay, so juveniles just kids. Adults are just... Okay, fine. In a study, the numbers of juvenile adult chimpanzees were estimated at the start of each year, and a model for the population satisfies this matrix system. Okay, where A is a constant, Jn and An are the respective numbers of juvenile and adult chimpanzees n years after the study. Okay, interpret the meaning of the constant A in the context of this model. Right, okay, so I don't know, let's expand this out and see what's happening. So for the top line, I'll do this over here. I've got j of n plus 1 equals, I've got a times jn, so a jn plus 0.15 times, okay, so 0.15 an. Right, okay, interesting. And then for a of n plus 1, we're going to have 0.08 times by this, so 0.08 times by j of n plus 0.82 of a of n, 0.82 of an. Right. Okay. let's think about this. What does this mean? Right, this means that the juveniles the next year, is this in years? Yeah, next year's, there's going to be some amount of juveniles that stay alive or stay kids because they haven't grown up yet. And then this is saying that the adults, that 15% of the adults will reproduce, or rather the amount of new chimpanzees is proportional to the amount of adults at the rate of 15%. So if there was 100 adults, and they should have produced 15 babies that year between them. That's what that's saying, I believe. And then if you look at, okay, so this is saying, this is kind of like a birth rate for adults. This is the rate of kids staying kids or just staying alive. You know, they might die, you know, childhood thing. It's the kids who make it to the next year and stay kids. And if I look at the next system of equations, then the adults next year, 0.08. Okay, so roughly this is saying approximately 8% of the kids or juveniles mature into adults. So if there's 100 for every 100 kids for a particular year, 8 of those kids out of 100 will grow up into adults in that particular year, or they'll be classified as adults at that point. And then rather worryingly, and then 0.82, that kind of means that only 82% of the original adults from the previous year survive. So you've got a death rate of about 18% of the adults every year. That's a bit worrying. So I kind of feel that interpret the meaning of the constant A in the context of the model, I feel like I've interpreted all 4 of the things in this model, well, all 6. So this is the juveniles. This is juveniles of some next year, and this is the adults of some next year. Okay. Yeah, I feel like I've explained all 6 of them, to be honest. So this is the juveniles for the next year, and we're saying that it's the juveniles of the previous year times by A, where A seems to be a rate of which either the kids are staying kids or they're staying alive, they're not dying. And then plus, and then adding 0.15 of the adults. Now, it doesn't make sense for adults to be turning into kids, but what might be happening is for every 100 adults, then they are producing 15 juvenile babies. Oh, my vacuum's just about to go off. Sorry, back in a mo. Okay, yeah, sorry about that. So where was I? I've explained A. Okay, at the start of the study, the total number of chimpanzees in the country was estimated to be 64,000. Okay. So the start. Okay, so that means JO plus AO is 64,000. Okay, we don't know how that's split up, I don't think. Does it say? According to the model, after 1 year, the number of juvenile chimpanzees. Okay, so then J1 equals 15,360 and A1 equals 43,008. Just adding those 2 together, 15,360 plus 43,008 gives 58,368. I'll do it, they're going down a little bit. Okay, find in terms of A, right, the inverse. Okay, so, no, we've done this many times. So you swap these 2 over. So this is going to be 0.82 with an A down there, and then you make the opposite corners negative, so it's 0.15, and that's 0.08. And then remember to multiply that by 1 over the determinant, so it's going to be 0.82 minus the other product, so 0.15 times 0.08, which is going to be 0.012. Okay, there's my inverse. Okay, that wasn't bad. And then hence or otherwise find A. Okay, so right. Okay, so if I apply, okay, so J, okay, that's new page, maybe. Okay, new page. So I've got J1, I've got A0, I've got my matrix. No, not A0, I've got A1. I know what these two things are, that's fine. And I've got the matrix is A 0.15, 0.08, 0.82, and this is times by J0, A0. Right. What do I know? Well, I know that. Right, I know a couple of things actually. I know that A0 is the same as 64,000 minus J0 because these two have to add up to 64,000 because that's how many there were initially. I know what J1 and A1 are now, so that J1 is, what is it, 15,360, and A1 is what, 43,008? So, I mean, I could. I've got two simultaneous equations. Do I need to use the inverse? Well, I could have done, in all fairness. The reason why I'm not going to use the inverse... Oh, should I? No, I won't, because it just looks a bit more... This looks a lot easier to solve. So what I've actually got is A times by J0. So A J0 plus 0.15 times this. So what's 0.15 times by 64? Okay, so that's 9,600 minus 0.15 J0, and this equals 15,360, and I've got 43,008 equals to 0.08 J0 plus 0.82 times by 64,000, which is 52,480 minus 0.82 J0. Okay, well, it looks like I can use the second equation to work out what J0 is, and then I can sub that into the top one to work out what A is, right? That doesn't seem too bad. So, what is 0.08 minus 0.82? Okay, so I've got minus 0.74 J0 on the right-hand side from this equation, and 43,008 minus the 52,480 gives minus 9,472. So all I have to do is that answer divided by minus 0.74. So I get the juveniles in the first year are 12,800. Interesting. So all I need to do now is whack it into the top. So the first one, so I've now got 15,360 equals A times the amount of juveniles, which is 12,800 from the previous bit, plus 9,600 minus, and then that answer times by 0.15 will give 1,920. If I add that to the other side, I get over here 17,218. If I minus 9,600, I get 7,680 equals 12,800A. So if I divide that answer by 12,800, I get A is 0.6. Groovy. That wasn't too bad. Calculate the change in number of juvenile chimpanzees in the first year of the study. Right, so what was it? So J0 was 12,800. And it's going to J1 is 15,360. So 15,360 minus 12,800 means it's increased by 2,560. Okay, given that the number of juvenile chimpanzees is known to be in decline in the country, comment on the short-term suitability. Well, lol, short-term, this is not suitable as model predicts a short-term increase in juveniles. And that's not what's actually happening. So the model actually predicts that the juveniles will increase by 2,560 in the first year, but it's known that they're going down. So that's not a particularly good model in the short term. Maybe it stabilizes and long term, it doesn't grow or it starts to decline, but short term is definitely a problem. Anyway, a study of the population revealed that adult chimpanzees stop reproducing at the age of 40. Redefine the matrix system for the model to reflect this information, giving a reason for your answer. Okay. Right. So it looks like there's babies, there's juveniles, there's adults, and now there's old people. And they stop after 40 years. Okay. Right. So let's think about this. So there's going to be the juveniles. Juveniles n+1, there's the adults moving on n+1, and now there's the old people, or I would say pensioners, but the one, they haven't worked, and two, I don't really want to spell Jap, but never mind, JO is fine, and they're the next ones on. Right, now we still have to preserve what's going on here. And this is still going to be J of n. This is not J A of n. This is going to be J of n. This is going to be A of n. This is going to be O of n. Right, now what would preserve? Well, what did we say? 8%. Okay, I think the only thing that's going to stay true is this 8% of kids going into adults, isn't it? So I think this is still going to be 0.8 still. Well, let's think about it. J of n, this goes to there. So that's going to be some constant, right? That's, yeah. The amount of kids that stay kids is going to be some constant A. I'm guessing that's still 0.6. So that's not going to change. The amount of kids that stay kids, I don't think kids staying kids or kids surviving the next year is going to be too heavily influenced by adults becoming infertile. Whatever. I'll tell you what, let's move this over. This needs to be a 3x3. Okay, and then in this column, this is when we have this times by adults. So that's proportion of, or I don't know, let's that be a new, not A. Let's call this alpha, so some new constant. Don't really care what it is. Would it not be the same as before? Maybe. Could be 0.15. And then the amount of kids, this times this, well, since the old people, the old rank, what are these, monkeys, chimpanzees? Since the old chimpanzees don't contribute, this has to be a 0. I think that's that row done. And then if we look at the amount of adults, well, the 0.08, the juveniles has to be 0.08 again, because I thought that was because the maturity of kids to adults. Well, hold on. This is going to be 0 as well, because this is the 0 times by the old people. Oh, maybe old people is not a good idea. Let's, instead of O, because that'll be confused with 0, let's call it E for elderly. the amount of elderly people are not going to contribute to the adults. The amount of adults contributing to adults. Or is that not going to be the same rate? Well, it's going to change, isn't it? Because some adults are going to become seniors. I don't know. We'll call that K. And then for last one, we want the adults. Well, this times juniors. Well, there's no juveniles become elderly people. That doesn't make sense. That has to be a 0. And then this one has to be there to there. So the amount of adults. Well, this could be a different rate. Let's call it L. And then for the last one, it's the amount of elderly people that stay elderly, or the amount that die. Let's call this capital M. So I think the only constants we can kind of be sure of are these. We don't know what these constants are, and these constants have to be a 0 for the reasons I've stated. So this 0 is because no elderly chimps make babies. This is 0 is because no elderlies create adults, because that's not how time works. And this is a 0 because no juveniles become elderly first. They've got to become adults first. Okay, so definitely these are 0s, there's 0s, and the rest are constants. You could argue that the rest are a bit undefined. But yeah, no, interesting question. It's a matrices modelling question. Very interesting. So yeah, hopefully you guys enjoyed that. If you have a Casio FX991EX, that's great. If not, don't worry. It just probably means you've got more work to do. But yeah, hope you enjoyed it. Peace out.